All right, so we are going to get started going over some stuff on phases and phase changes today, what you need to know about solids, liquids, and gases, and various endo-exothermic phase changes. All right, so first off, just when we talk about phases and phase changes, potential and kinetic energy are going to be involved, and you're going to see this discussion kind of roll on as you move through this unit. So a physical state called a phase is a distinct homogeneous part of a system. So we're talking about solids, liquids, and gases. Now, and the relationship between potential and kinetic energy is going to influence the phase that those particles are going to be in. So one little thing is that we're going to see potential energy is really going to be in the form of our intermolecular forces of attraction between particles. And according to Coulomb's law, we know that electrostatic potential energy is going to, like the strength of the attraction, is going to depend on the charges of the particles involved, the distances between them. So Coulomb's law is going to come right back into play with this unit. We're also going to be talking about the role of kinetic energy. Kinetic energy is associated with the random motion of particles. So it's related to the molecule's average speed and it's proportional to its absolute temperature. So one little thing that we'll touch on shortly in this unit is with kinetic energy, it's really related to temperature. So as kinetic energy increases, temperature is going to increase. So temperature is a measure of average kinetic energy. So you might want to add that in. It will show up in your notes later on. So a measure of average kinetic energy is your temperature. So just keep that in mind as we move forward. All right, so you do need to know the differences between solids, liquids, and gases in terms of particle arrangements, different properties of each of those phases. So let's just start with a gas. So these ones, the particles are spread out far from each other. You can see the space. They completely fill the space that they're placed into their volume. So you can see from the textbooks, it talks about total disorder, much empty space between them. They have complete freedom of motion, and the particles are far apart. And you should be able to describe that or draw that in your diagram. One little extra thing is that the potential energy is pretty small relative to the kinetic energy at that point, because of how fast the particles are moving, and the fact that they've completely overcome the attractions between them. With a liquid, the particles are going to take the shape of the container that they're in. However, it has that fixed volume, so it doesn't take up the whole container's space. So there's disorder. The particles or clusters of particles are free to move relative to each other. The particles are close together. So they are close together, but they're able to flow around each other, unlike what we're going to see in a solid. Also keep in mind that attractions are stronger, particles are in contact with each other, they have enough energy to move randomly around each other, which is again going to distinguish it from a gas and from a solid. And then lastly, we're going to start by talking about the crystalline solid, which has a very ordered arrangement. We'll distinguish that from like an amorphous solid in a later lesson. So it's an order arrangement. Particles are essentially in fixed position, close together. The attractions dominate the motion, so much of the particles are fixed in position relative to each other. Just make sure when you're practicing and going through different questions that you can draw this yourself. So I usually say, like with a gas, it's going to look very much like the picture, far apart from each other, taking up the whole container. If I draw a liquid, I'm going to keep them all kind of at the bottom, disordered, close together. And then as a solid, I'm going to actually keep those nice, neat rows. I usually keep it right in the middle, just so I know that someone looking at it can tell the difference between my gas, my liquid, and especially the difference between a liquid and a solid based on how you draw those particles. This is just a little table from the book that I would make sure you feel comfortable with. In terms of shape and volume, you will see this terminology from like Regents questions, where we will talk about how a gas has an indefinite volume and shape, meaning that they can both change. A liquid would be an indefinite shape because it can change, and then it has a definite volume, meaning the volume that can't change. And then finally, with a solid, you have a definite shape and volume, both cannot change. So just terminology I want you to be aware of. And you can read through that from the textbook. In terms of compressibility, it's really just the gases that have a high ability to be compressed and pushed together, and that's because of all the space that's between them. And then in terms of their ability to flow and move, gases have the highest. Liquids are moderate in the sense of they can flow around each other. And then in terms of solids, they don't flow, they're only going to vibrate in place. Okay, because as long as you're not at absolute zero, all of those are going to have some motion, including solids. All right, let's get into phase changes then. So we have both endo and exothermic phase changes. We haven't dealt too much with energy yet in our curriculum. So this is going to come into play a lot in this unit and in our following unit. So with our phase changes, one little thing to keep in mind that we haven't talked about is that during a change in temperature, that we're going to be changing the amount of kinetic energy. And that's when we have a pure solid, a pure liquid, or pure gas. When we undergo a phase change, though, which is what we're dealing with now, temperature is always going to remain the same. So because of that, changes in phase are result in changes in the potential stored energy, which really just has to do with the particle interactions. So a couple of things first with this, before we get into endo and exothermic, is just remembering and identifying the different phase changes. You guys know, like, solid to liquid is freezing, liquid to solid is melting, liquid to gas would be vaporizing, which can include boiling, which is underneath the surface, or evaporating, which is at the surface. Both fall under vaporization. Or gas back to liquid would be condensation. The two that you might not be aware of as well is that a solid going directly to a gas is going to be sublimation, this one down here. And then a gas going directly to a solid is going to be deposition. So sublimation would be dry ice going directly into a vapor. A gas into a solid, I always point out, like, if you were to sit in your car tonight all night long watching your windshield, the water vapor in the air would go directly to a solid as it hit your windshield. So that's one basic example of deposition that you may be aware of. So what are the big differences, or the two categories of these phase changes? So one is our exothermic phase changes. So when you see exothermic, think of exit. So heat is going to exit out. So how this occurs is, if you look up here, or over to your right, what ends up happening is as heat leaves the material, those attractive forces between the particles that we've talked a little bit about, and we're going to talk a lot about the next few days, are going to be able to pull the particles closer together. So exothermic phase changes are going to be when you have a gas going to a liquid, going to a solid. Those are all your exothermic phase changes. So condensing, freezing, deposition. Because again, heat's going to leave the material, and then the particles' attractions are going to pull them back together or closer together. And being aware of which of those are exothermic is going to be important. Our endothermic phase changes are the opposite. Endo, think of into, heat's going into the material. Okay, if you hold an ice cube, you guys know that the heat from your hand is causing it to melt. And that's because the particles, those liquid particles, are absorbing the heat from your hand, and then they're able to, in this case, overcome attractions, and then they move farther away. So this little part down here, when we talk about our endothermic phase changes, you're talking about particles overcoming attractive forces and moving farther away from each other because of that extra energy that they've absorbed. So all of our endothermic phase changes are going to involve moving particles farther apart. So solid going to a liquid, going to a gas. And again, also involving sublimation, that solid to a gas. Okay, so make sure and spend the time understanding which are your exothermic and endothermic. And again, we're going to build on this a lot over the next couple of lessons. All right, as we move into one last little part, has to do with calculating energy that's involved with these different phase changes. We haven't talked about calorimetry yet, or specific heat, so that will come in. So we're just focusing on our phase changes right now. So for a pure substance, each phase change is accompanied by what we call a standard enthalpy change, which may or may not highlight for me. There we go. Which is sometimes given in units of kilojoules per mole, or you'll see joules per gram. So heat of fusion is involved for both melting and freezing. So you can see heat of fusion for melting at 0 degrees Celsius and heat of fusion for freezing at 0 degrees Celsius. They have the same magnitude, just opposite sign. So if we're talking about melting, we're going to be using this positive value of either 6.02 kilojoules per mole, which is also we can use if we're involving moles, or we can use 334 joules per gram. So depending on whatever unit you're working with, an amount of energy will kind of influence which one you pick. The only difference for freezing is just that it's going to be negative. That we're going to plug in. And this will deal with that idea of it's releasing energy because of the exothermic phase change that freezing undergoes. Okay, for vaporization, it is so we just talked about our heat of fusion. We also have a heat of vaporization. So heat of fusion is H with a little f, and then heat of vaporization is H with a little v there. And what that's going to do in this case is going to be when we're vaporizing water or condensing water. So if we are vaporizing water, we are going to use 40.7 kilojoules per mole, or depending on if we're dealing with grams, we're going to have 2,260 joules per gram. Okay, and again, we're going to also use this for when we're condensing water. Okay, again, same magnitude, we're just going to be plugging in a negative to represent the fact that heat is going to be lost or given off from the substance. Okay, one little thing just to keep in mind is that even though we have our phase change temperatures here, the equations we're going to use do not have temperature in them. So it's just extra information understanding what temperature these phase changes are undergoing the change at, but they're not actually involved with the equation because temperature does not change that entire time that phase change is occurring. So where those constants will come in, I'll show you the equation shortly. One other little piece of this to understand is that when we looked at like water, you will see, and I'm just going to pick the 334 kilojoules per gram. So the heat of fusion for water was 334 joules per gram. And if we look at its heat of vaporization, it's 2,260 joules per gram. Okay, the heat of vaporization just about for every substance is greater than its heat of fusion. And that has to do with when I'm going from a solid to a liquid, I'm just overcoming the attraction slightly. I'm just getting them a little bit farther apart from each other, still keeping them close so that they can move around each other and move around in their relative positions. When I'm talking going from a liquid to a gas, I'm talking about completely overcoming IMFs so that they can move freely from each other and spread out from each other. This takes a lot more energy in order to accomplish. So that's why that heat of vaporization is going to be larger, and you should be aware of how to explain that as well. One other little piece tied in with this heat of fusion, heat of vaporization has to do with heat of sublimation. I would put a big star next to this to make sure you go back over it. And the idea here is that since sublimation is considered a combination of melting and vaporizing steps, under Hess's law, which we're going to talk about in a few weeks, says that the heat of sublimation is equal to the sum of the heat of fusion and heat of vaporizations. And I've actually seen a question where you've had to add these values together in order to get that. So the heat of sublimation is going to be that heat of fusion plus the heat of vaporization. Okay, and that little notch there up in the top part is just at standard conditions that we'll talk about. All right, just a little bit more. This is just the summary of the phase changes and their enthalpy changes in terms of our endothermic ones, which are increasing the energy where it's absorbing heat. So moving in, this direction here. Oh my goodness, sorry. Moving in this direction. And then all of our exothermic ones, which are moving down in terms of enthalpy, and just showing you the relationships between the two. All right, and then lastly, how we're going to use those heat of fusion and heat of vaporization is just in these formulas that you see in front of you. This allows us to calculate the amount of heat that's either absorbed or released during a phase change. You'll see these top two are just dealing with the number of moles. So because of that, we're going to use the heat of fusion, heat of vaporization in kilojoules per mole. And that's where the N is in there. And then in the bottom ones is when we're involving mass in grams. And again, that means that the heat of fusion, heat of vaporization, we need to be reflecting or picking the one that involves the joules per gram in that case. All right, I know that was a lot of information, but take some time and look back over it. You're going to do some practice questions on the phases and phase changes, and also start practicing some of the calculations we just went over.